Welcome everyone to today's session. We're really excited and there's a lot of great information. So we're going to try to get right to our great presentation. So I'm going to hand it over to Kevin to introduce our speaker and we're just going to get started.
All right, thank you very much. I'm Kevin Brennan with Source 2050 and co-host here at Passive House Accelerator Live. Uh, if you guys don't know who Gary Klein is, he's our four-time repeat presenter here at construction for Passive House Live and the Passive House Accelerator events. He is always bringing the heat in the hot water, and he is a great contributor. I have spent many of evenings at summer camp listening to Gary's nuances about hot water, and still blows my mind that over all these years we still don't really have that much uh, groundbreaking improvements on hot water in most of our buildings. So Gary's been spitting the knowledge out for years. I've been listening, and let's see the work happening. Passive house is the largest load after you deal with the enclosure is domestic hot water in these types of buildings. So it's our frontier, it's our challenges. So no further ado, Gary Klein, welcome to the stage. Two things. If you have any questions as far as clarifying questions, please just type them in the chat, and we'll try and introduce or segment the presentation just so that we can clarify those issues. And then, if you can, kindly in the chat, just put in here why you're here today. What do you want to learn? What's your purpose for being here? So, without that to do, Gary, the stage is yours. Thank you.
Thank you very much. Can you hear me, Kevin, still? We're good?
Loud and yes, sir.
Great. I recognize several of you on today's call. I know I've helped some of you in various projects, so enjoy today's presentation. If I don't say something you know I'm supposed to say, be sure to ask that as a question. We'll do our best to cover it all. All right, so here we go. You should be seeing my screen.
Looks perfect. Looks good.
Great. All right, so I'm going to lay the issue of better performance on floor plans. How many of you have ever lived in a house where the water heater is on one corner and the furthest fixture is in diagonally opposite corner up a couple of flights? Maybe you still live there and you wonder why it takes so long to get hot water. This is the question that got me started over 30 years ago. Why did it take so long? And in fact, why did it take more than twice the volume of water that was in the pipe before the hot water actually arrived? And over 30 years ago, I decided it was time for somebody to start looking at hot water as a system. Everybody else was looking at building as a system and not talking about hot water. And a pretty quick analysis in the 1990s told me what Kevin just told you, that water heating is either the first or second largest thermal load in most residential occupancies. It was true then. It was true for apartments then. It hasn't gotten better because we're not focused on the system. And that's the point of today's conversation. It's a systems issue, not a component issue, which is why you don't see me on 2050. I can't sell you anything. I can sell you an idea. And so that's what we're doing today. We're going to share this idea. All right, what are we aiming for? People want their showers to feel right. They want their toilets to flush first time every time. They want clean clothes, dishes, and bodies. My shorthand version is they want hot water, the service of hot water as efficiently as possible. And the two key things they want are hot water now and never run out of my shower. Does that sound about right to everybody? You should all recognize that I've interviewed over 50,000 people in the last 30 years of my work, all about hot water. And yes, they've shown up in a room where I'm speaking, but I would say you're legitimate users of hot water. This experience is not abnormal for most of us here in the US. And I don't think it makes sense to discuss efficiency until the desired service has been provided. So we're going to spend time on figuring out what the target is and then how to achieve it. And if you agree with the target, then stop whining about how difficult it is to achieve it. You've got to decide on the target. If you know what you want to hit, you're going to aim for it. All right. So we're going to talk about best practices. Looks like I have some interesting things. First, reduce the time to tap. There's two parts: reduce the distance from the source to the use and right-size the piping based on modern information. Part two is reduce the pressure drop in the pipe and fittings, and in the faucets and the shower valves. We're going to cover that. And the third item is improve the performance of faucets and shower heads. Okay, and we're going to talk about all of that. All right, reduce the distance from the source to the use. The shorter the pipe, the less time it takes. But so the same is true, the smaller the pipe diameter, the less time it takes. All right, why do we have 3/4 inch pipe or 1/2 inch pipe? And you're going to tell me because the code says so. Well, the rules for our codes were written a long time ago, and we ought to rethink some of the sizing. The lower the flow rate, the longer it takes. How many of you specified low flow fixtures because it was part of some program, including Passive House? Right? Come on, we've all done it. Guess what? If you cut the flow rate from 2 gallons a minute to 1 gallon a minute because it said to, and you got points for doing it, you double the time it took for hot water to arrive because you didn't change the piping. If you change the flow rate, you should change the piping to match it. And it needs to be done. And so my question is, how long is too long? All right, I'm going to do something a little fun about this. I need you to raise your virtual hands. How many think they'd like to have hot water arrive within 1 minute? Raise your hands. How many would like it to arrive within 30 seconds? How about 15 seconds? How about 10 seconds? How about 5 seconds? How about 1 second? Anybody for the 1 second case? It's really hard to do. It can be done, but it's expensive because you have to plan your system better. Okay, and we rarely are able to do that. It's a practical plumbing question. All right, we have to make a decision of what we're going to aim for. All right, and we'll come back to that a little bit later. They start with deciding how long we want people to wait. The decision on the location of the wet rooms and the mechanical spaces are made by an architect. They define horizontal distance. Okay, horizontal distance is really big in plumbing terms. Better floor plans lead to better hot water performance, and better floor plans decrease the residence time of the water and the plumbing, hot and cold. And I'm going to come back to that later in the presentation today. So the best hot water distribution system, ideal, has the smallest volume in the pipe from the source to the use. Sometimes the source is a water heater and sometimes it's a recirculation trunk line. Does that make sense to everybody? Sometimes we do heat trace for the line, but sometimes it's a pipe and sometimes it's the water heater. It depends how you planned your plumbing. And for a given layout, you want the shortest buildable trunk. I don't like branches because branches tend to be fatter than twigs. If the branch and the twig can be the same diameter, then I don't care exactly, as long as they're the right volume in total. You want the shortest buildable twigs, the fewest plumbing restrictions, and you want continuous insulation. Does continuous insulation on a hot water pipe sound a lot like continuous insulation on the envelope of the building? It's an identical process. I've been working in parallel with all of you on the envelope stuff to figure out how to make water heating work right. Okay? The same rules apply. Heat transfer is heat transfer. And these rules for system design apply to cold water piping too. You want to actually reduce the volume in the cold water side of the building as much as practical as well, for other reasons, but nonetheless, you want to do it. Okay? So the challenge, I want you to deliver hot water to every outlet, wasting no more energy than we currently waste running down the drain and wasting no more than 1 cup waiting for the hot water to arrive. How would you do it? Put your answers in the chat. Someone will read them to me. What do we see? Kevin, anything?
I'm looking now, Gary. Sorry.
There's nothing
It's
in the
okay.
chat.
Well, that means no one's paying attention. I guess we're
Someone
done.
said water manifolds.
Okay, so manifolds. Okay, that's one
Put
possible
all the
answer.
taps close together.
Yeah, that's a good one.
Instantaneous heating at the point of use.
That probably doesn't
Local.
do what you think it's going to do. It's local heating, but go ahead. What else?
Recirculating pumps, POU.
Point
Sorry,
of
Kevin,
use.
I stole your thunder here. Centralize all taps near water heater.
Okay, so it turns out there's only 5 answers. There aren't 6, there's only 5. We've been looking for 30 years, so we're pretty sure about our assessment here. But the key in all cases, however you physically choose to implement it, is to make sure that you have less than a cup of water in the pipe between the source and the use. So the question then becomes, how long is a cup? Well, it depends on the diameter of the pipe. Why would you pick a certain diameter? Because it should be matching the flow rate of the fixture you're attaching it to. Okay. And so trunks tend to be big diameters, branches seem to be medium diameters, and twigs seem to be the smallest diameters. And they should be, because they're proportional to the size, the flow rate of the fixture that they're serving. If you serve more than one fixture at the same time, you might need a bigger pipe. That's an interesting question. So there's a calculation for this, but one of the things we learned, and we learned this to beginning in 1992 or so, was that more water than is in a pipe comes out before hot water hot enough to wash dishes or bathe in comes out. How much more? Anyone want to hazard a guess? I didn't know. When we first did this experiment in the 1990s, I had no clue. And what we found out is that Carl Hiller has measured it in the early 2000s for 3/8 to 3/4 inch pipe, and Yonder reviewed the data in 2018 for flow rates in the same pipes. And we found out that roughly 1.5 to 2.5 times the volume of water comes out of the pipe before hot water arrives. So if you have 1 cup in the pipe, 2 cups are going to be coming out of the pipe before hot water hot enough to meet the need of 105 to 110 comes out of the pipe. How many of you ever turned on a tap, like a kitchen sink, to rinse something, and you've lifted the handle, the single lever up about halfway, right in the center, so you get half hot, half cold, half flow? Anybody ever done that? You just trigger an event at the water heater that will never reach the sink, because you turn it off in 5 to 10 seconds. It's not long enough to arrive. The pipe's too long, too much volume. And so we have to figure out what we mean by providing hot water. And I'm going to contend that in most cases, most of us care about hot water hot enough for washing dishes at the sink in the kitchen and for bathing in the bathroom. Most of the time, we don't use hot water for rinsing our hands when we wash them. We want it warm enough so we don't freeze them, but it doesn't necessarily have to be 105 or more. In fact, you can't put your hands in 105 easily for very long. Okay? Just doesn't work well. So we need to decide what's acceptable, and you work backwards to find the maximum valuable life value you want to have in the pipe. So if you want the hot water to arrive within 10 seconds, you can't have more than 10 seconds of volume. I'm conflating volume and distance and time because they're all interchangeable to me. You tell me one, I'll back calculate the others. I don't need two. With one, I can tell you what the numbers have to be in the range of. And so it turns out if you really want to get hot water, like the temperature of the water heater, it takes 3 to 5 times the volume that's in the pipe. So here's a table that helps us figure this out. The American Society of Plumbing Engineers published some guidance in 2003. I don't think it's changed since, that acceptable performance is to deliver hot water within 10 seconds at every fixture. Does that sound like a pretty good target? Right? From your hand raising, that's a pretty good number, right? Everyone would like to have it within 10 seconds. So how would you build it? So I use 1 gallon per minute when I do my designs for a couple of reasons. One, most of our fixture flow rates are actually around 1 gallon per minute on the hot side today. Okay, even 2 gallon per minute shower heads have only 1.5 gallons at hot. Okay, it's just because of proportioning of things. So I use 1 gallon a minute because it's roughly what we're at now, and nobody cares if hot water gets there quicker. So if you design for 1 gallon a minute, you're sort of future-proofing your building, assuming fixture flow rates go down, which they tend to do as things get clogged. And you may or may not be able to buy 2.5 gallon per minute fixture flow rates sometime in the future. So I decide to get there quicker. It's just a design choice. If you tell me that you're going to use really low flow rate stuff, I start using 1/4 gallon per minute columns. Okay, just because that's the next best number I've got available to use. If you want to go lower than that, call me. We'll talk about what it means. So here's the kicker. It turns out that if you want hot water to arrive within 10 seconds at 1 gallon a minute, you can't have more than, you can't see it, but 10 ounces of water in the pipe. 8 ounces gives you 8 seconds. So how long is 8 ounces? I don't want to discuss anything that's not in the green. We're talking about how to do it right. Let's talk about how to do it right. So here's the lengths. So let's see, 1/2 inch is usually the minimum allowed by code for fixture branches, what I call twigs. It's somewhere around 5 feet. And you know anybody who's about 5'2"? They're the height of 1 cup of water and 1/2 inch copper, type L. And you know anybody who's basketball, 6'6" or so, 6'5"? Guess what? They're the height of 1 cup of water and 1/2 inch plastic pipe. There you go. We're all about the height of 1 cup of water. And my best practice is to allow no more than 2 cups in the pipe from the source to the use. Why 2 cups? If you build on slab, you don't want to put your plumbing under the slab. You want to bring it from the ceiling down. And the length from the ceiling down to the angle stop for the faucets is around 8 to 10 feet. And I need that much height to bring the water from the ceiling down, so I don't have to extra special bring my loop down the wall or my source down the wall. That's why I give it. It's a practical plumbing exercise. You get 2 cups in the pipe, which means you should expect 1 quart before hot water arrives, which back to here means it's going to be 15 seconds. Anything you can do to get it better is better, but that's at 1/2 inch pipe. What if I could use 3/8 pipe? Well, in copper, I go up 50%, 60%, and in PEX, I roughly double the length. So I'd get my 12 feet, but be closer to a cup if I could use 3/8 twigs. Does that make sense to everybody? Most of you know Allison Bales down in Atlanta. And Allison and I looked at his 1/4 inch tubing while I was there last January. I don't have 1/4 inch on here. I'll have to update the table, but 1/4 inch is approximately 1 cup is 25 feet. But you can't use 1/4 inch tubing for high flow rates. Why? It's very restrictive. It has a lot of friction loss. All right, moving on. Now, we've talked about the time to tap problem. So I was at a conference some years ago out here in California, what was called then the Dry Climate Forum. And I had a conversation with the Habitat for Humanity builder in Stockton about his plumbing layout. And when he started, his plumbing layout was at 80% of the floor plan area, okay? Of this hot water rectangle, a hot water box. What we mean is that's the relationship between the water heater, right, and all of the fixtures. In his original case, the water heater was here in the garage and the fixtures are spread all over the house. So he had about an 80% ratio. So far, so good. When he came back a year later, and depending on how you look at it, he was down to 4% of the floor area was related to his hot water system. All of the angle stops, all the valves, everything was in that box, the wet wall for the plumbing. 2 years later, he came down to 0.8%. He's down to less than 1% for 2 bathrooms, a laundry room, and a kitchen. That's not much area attached to water, is it? By the way, that's his cold water system too. Think about it. All of the plumbing's concentrated on that wall, and it was volunteer labor, so the less feet of pipe you had to pull, the quicker the volunteers could get their job done. By the way, that'd be true for labor on a job site that's getting paid. Either way, it's less. Fewer connections, fewer potential for leaks. Everything is concentrated in one plumbing wall, not 5 of them. I just saved floor area, didn't I? By concentrating it into one wall. So what I have one 8-inch wide wall. It's only 10 feet long. Who cares? We waste a lot of space in other ways. So that's the best 1 story so far in the country that I'm aware of. And the best 2 story we actually all own a piece of. This is at NIST in Gaithersburg, Maryland. You all probably know the architect, Betsy Pettit, and I didn't know she designed it, and I went to look at it, and then I found out, and I called her and said, by the way, this is the best I've seen so far. Okay, and it's still true. She got this 2,700 square foot house to have a rectangle that's relatively small for the size of the house. So 10% is a really good target for floor plan areas. How's that sound? Better is better. Less than that is better. So how do you have the common hot water relationships and hot water systems? What we typically have is trunk and branch. This is a single trunk long with branches that go off of it. and it's inconsistent times to tap. That's what we often have, and relatively long to the furthest fixture. This is a um, two trunks, two branches off of a main trunk, right? And so this is what you do when you do the addition above the garage or out the back. This is often what we see when they split the house from the middle to the sides, up and down. And again, it's inconsistent times to tap, and the potential to be water, energy, and time efficient is low because you've got inconsistent answers and you've got the water heater at one end and the fixtures far away. These are high potential for being water, energy, and time efficient. If you have a relatively small loop with short twigs, no branches, you see that I got rid of them. And it's low if you have long loop and continuous pumping. The energy goes up as the loop runs longer. Okay. And then this is another way of putting the water heater closer. And so you can see what that's going to be, right? This is a high potential for water, energy, and time efficient, where you've split the plumbing into more than one part with two water heaters for each part, one for each part. And it's low if you have a home run manifold with long twigs, because you haven't solved the problem of time to tap. Okay. All right, next slide. Oops. Now we're going to right size the pipe. The first thing was distance. Distance is the architect's problem. It's a layout function. All right. How do you right size the plumbing? Well, there's different methods to determine peak flow rate and sizing. And most of us in the country are using something from the International Code Council, IRC or plumbing, or IPC, local adoption as amended. Some jurisdictions use the Uniform Plumbing Code from IAPMO. And in the Uniform Plumbing Code, there's Appendix M. We're going to talk about that. Others use other methods. Okay. I don't care which method you use, we need to bring the method into the modern era. Whoops, I just stopped sharing, my fault.
Gary, while you get your screen back up, you're at about halftime, just so you know.
Thank you. I'm going to keep moving. All right. So we want to improve estimates of peak flow rates. You want to, if you're designing a new building, you should measure flow rates in a similar occupancy before designing the new building. You want to use modern peak flow rate estimation tools for mains and branches. You want to match them to modern flow rates and probability of the simultaneous use. And twigs, you want to match the flow rate of the fixture or appliance that they're attached. You want to select flow pipe sizes that optimize velocities and residual pressures. You need a certain amount of, you shouldn't have too high a velocity for continuous flow situations. And you want to make sure you have enough residual, you want to have enough velocity to clear out any particulates that settle in the pipe. But you want to make sure, most importantly, that you have residual pressure for everything to work right. We'll come to that a little bit later in the presentation. So the Uniform Plumbing Code came out with the Water Demand Calculator in 2018. In 2017, it was published in the We Stand, and there will be a standard coming out later this year just on the Water Demand Calculator as a standalone document, so you can reference it. Most of our methods today use water supply fixture units. The values date from the 1940s, and they're not tied to actual flow rates. The Water Demand Calculator allows us to tie information to the exact, the flow rates you intend to use, and then you get to evaluate what happens in the pipe sizing. To show you an example, this is, I think, 20 some odd buildings here, 22 buildings. And what we've found is that these little black dots are the flow rates. 99 percentile measured flow rates. The plumbing code predicts this value. And here's the real flow rates. We're looking down here in this corner, and you can actually see the letters now, but they're nowhere near what the code predicts. So the code predicts really high demand, and we're just not getting it. And that's a real problem. This is more specific information. You can see that some of the units, some of the predictions for the code are way off the chart. But in all cases, the Water Demand Calculator is predicting a safety factor for up to 2 to 6 times instead of 5 to 20 times. Right? Code is overestimating the peak demand by an order of magnitude, and here we're trying to get it in a factor of 2, which is still a good margin of safety. What we found from all of our analyses, both the real buildings and modeled buildings, is somewhere in that $600 to $1,200 per apartment in first cost reductions. We found one job in Portland, which was garden apartment buildings. Because of the way the code was written there, they were being asked to put in a 4-inch main from the city, and that development costs were over $400,000. And when they right-sized it, their development costs went down so they got to save $400,000. Pretty amazing, right? That's $2,500 per apartment in first costs. Big numbers. Here's a report that we did for the state of California to get California to adopt the water demand calculator into its plumbing code. That tells you all about the math. All right, let's reduce pressure drop in pipe and fittings. This is fun for me. I got interested in this about 15 years ago, call it 2010. And I tried to figure out why we were using tables that seemed really old to me. And I found out that the data we use in all of our tables comes from the 1990 data. It comes from this Hydraulic Institute. They adopted it from Freeman in 1941, but Freeman was the son of the guy who did the research in 1892. And that's what we're using for pressure loss in pipe and fittings today. It's for steel pipe and threaded and flange fittings. That's not what we use. So I set up a pressure testing lab in Downey and then later in Arcata, both in California, so we could measure this. We've tested over 70 different combinations of pipe and fittings, so we could do the math properly. Here's some pictures of what we did. This is our discharge on the left. This is a section of straight pipe that we stretched out to be straight, around 20 feet long. These are our coils. This is a rectangular coil, so we have 10 elbows. Here's 10 elbows here that's not coiled, but it's hard piped. Here's we're testing what's going on the pressure loss through insert T's, and we're looking at a coil of pipe. We've tested all of this kind of stuff so we can figure out what's going on. We now have data for 70 different combinations. Here's the thing we need to pay attention to. Copper type, what is it? CTS. So the copper equivalent piping that we all use has the same outside diameter, but the inside diameter changes based on the wall thickness of the material. So copper, that's 100% of the available area. CPVC or PEX, it's around 76%. Cold expansion PEX with the insert fitting, it's around 50%. And if you don't have that cold expansion fitting and material, then you have a 25% inside diameter at each of the fittings. This tells you really clearly you want to minimize the number of fittings. In particular, I don't want to see elbows in any flexible tubing. You want to do bend supports. It's way better. We did this research based on target velocities. These velocities tell us a great deal. If you're trying to hit 8 feet per second, because that's what your code says your maximum is, these are the flow rates that you can have in that pipe. If you only want to have 5 feet per second, you have to be somewhere between 4 and 6, right, for hot water. These are the same problems that have to be solved for everybody. You want at least 3 feet per second in order to clear out sediments in your pipe. So you want to make sure that on a regular basis, you have more than a really low flow. We have a lot of fat pipe. All right, we want to reduce the pressure drop in the faucets and the shower valves. We took the same basic test rig. We went to the store, bought a whole bunch of common shower valve sets that we could find, and we put them on the rig. What I want you to see here is that there's restrictions of 2 types. The one is that you see the big hole? You've got 1/2-inch pipe connecting into the shower valve, right? See the big hole inside, the black hole inside? See here? This one's got a different size black hole, right? This is going down to the tub. This is where it goes back up to the shower. That hole is 3/16 in diameter. It's a great resistor, all right? Here's an example of another pathway. It comes in and the bypass goes around this space here. That's more than almost 3 inches long of 3/16 tubing. Huge restriction. In addition, there's restrictions in the mixer, but you need the mixer to prevent scalding. So you have to have that. And so we set up to test each of these systems using the same basic equipment we use for testing the pipe. And we have data on all of those too. This looks like a nice egg beater, but this is the way we tested it. All right. I want to improve the performance of faucets and shower heads. I want to utilize non-aerated stream patterns so that I can minimize aerosols. I want to install pressure independent flow regulators, and I would like to reduce backsplash. And I'm going to show you some fun stuff. So when we talk about faucet aerators, we usually mean the thing on the left, the champagne bubbles, all right? But all of these are the category, all of these stream patterns are actually flow regulators for faucets, but as a generic term, we call those aerators. We have flow regulators for showers. We have flow regulators for faucets. You can pick your pattern of use for the stream patterns. You can have aerated, laminar, or spray. These two do not allow air inside. And here's where you see it. You see this little gap right in the tip of the flow regulator? That's what lets air get in to the stream. These two do not have the aerated streams. This is for the solid laminar flow, and this is for this thing that looks like mini shower heads. So I want to see them be pressure independent. Everything before 2000 was pressure dependent. If you had high flow, you had high. If you had high pressure, you had high flow, low pressure, low flow. Pressure compensating orifices have become essentially available since around 2010 for sure, widely available. And today, more than 90% for shower heads and most many faucet aerators can be pressure compensating. And the pressure compensating says when I have low pressure, I can still have high flow. This graph shows the gray line. That's the normal pressure flow curve without compensation. And if you have 2 gallons a minute at 80 psi, you'll only have 1.4 at 40 and 1.0 at 20. And most of us in our buildings have between 20 and 60 psi. 80 is the maximum allowed by the code. If you have a single pressure compensating orifice, you see that rubber O-ring in the middle there. That O-ring allows you to get this compensated properly at one of them. You get more than 85% when your pressure is below around 20. And when you're at 40 or more, you get 98% of the rated flow. That's pretty good, right? Because we bought it to work right, and we just don't know what the pressure is going to be. And for faucet aerators, you can see the same idea. They're rated at 60 psi. I have no idea what they're rated at 2 different pressures. They sit 3 or 4 feet apart in most bathrooms. I just don't get it. But anyway, this is based on at 60 psi, and you get a single core. You see the single core. If you have a dual core, you get closer to the gold line. And that means you're getting something like 95, 98% of what you expect, 98% of what you expected to pay for at all pressures above 15 psi. That should be satisfying to everyone. And it turns out that as of last year, early 2025, all faucet flow regulators are now available in dual core from the company that makes 90-something% of the US market aerators, flow regulators. And this is really cool. This is a special pattern of flow from that same company. It's called NeoPearl. Their headquarters in the US are in Connecticut. You are able to fill your bathtub from the ceiling without splashing the water. They've created a stream that collapses in on itself. It's very cool. Looks like any other aerator. It's just, it's designed differently inside. And in addition, you want to aim the faucet away from the drain and away from the people so it doesn't bounce off to hit you. Okay? You're trying to not aerosolize stuff. If you're going to become old, you're going to become more potentially immune compromised. You better start paying attention to it. We want to make sure that we're not harming ourselves and our friends. And if you need to do scheduled maintenance, they come with color coding now. Pretty cool. You can decide which month you're in or which quarter you're in and just go through and replace them so you know where you are. All right. Best practices for heat pump water heater installations is one of the last things I have to cover today. My pet peeve for the last 3 years is the problem of blowing cold air around inside our buildings. We're taking outdoor equipment called a heat pump, and we're putting it on the top of a electric storage water heater, and we're using the air to create the heat. So you bring in warm air at 70-ish, and you discharge cold air at 60-ish. In most of the country, that's above the dew point. But what if the temperatures start to go down? Or what if you have high humidity air? We see that in the East Coast, for example, fairly frequently. If you blow that cold air around inside the building, you will eventually cause surfaces to go below the dew point and condensation will occur. And we spend a lot of time in our envelopes trying to prevent that. We need to do the same thing with our water heating. So the key things are to manage the cold air, exhaust air to prevent moisture issues, and you want to provide sufficient warm air so it runs in a COP above 2. My goal is always above 3, which means you have to have pretty warm air. And you need sort of a minimum airflow to make this happen. And we'll come back to those things. So here are some examples of what we have to manage. We have top intakes and side exhaust, top intakes and the other side exhaust, top intakes and rear exhaust, top intakes and top exhaust, top intake, side intakes and top exhausts. All of these are possible combinations, and you have to make sure that the air can go in and get out and the filters can be accessed. I've got lots of examples where they're not installed very well. I'd like to see that change. So where do you put water heaters? California, we like to put them in garages. Northeast, we like to put them in basements. The North, we put them in basements. Sometimes we see them in attics. Sometimes they're in a mechanical room in somebody's basement or a closet in the hall. There's probably other places. Some people put them outside. We don't usually do that much in the US. But I want to make sure that we get the cold air that's discharged from the most confined locations solved. We have to make sure we move the air safely so we don't constrain the airflow and we don't create potential health problems in the building. So what we've done here, we've got 3 examples. We have a side intake and a rear exhaust, top intake and a rear exhaust. I think this is what we picked on this one. This creates the largest closet we have to have. And what I tried to do is to say, okay, what space do I need in order to make the turns so I can get the air from out to get up? I don't want it to just blow around the closet, because if it leaks out the bottom as cold air, people's toes get annoyed in the winter. It's not good. I want to manage the airflow so it goes to a safe location. And so we've looked at it from a front view and a top view. The top view helps us determine the size of the closet. You need to make sure you've got space for service and access. It has to have a minimum in the front according to the codes. All that's good. Most closets have a lintel above the door. That space above the door to the ceiling is where I want to put the ducting. I want to use good commercial grills so that I can blow the air where I'd like it to go. I don't want it just to leak out of a bad hole. And I want to put in 2-inch pleated filters on the door. And because I had to have a wide door, 4 feet wide, I put in 2 doors because we don't typically make 4-foot wide doors. So we can get 2 and that'll work fine. If you put in better filters, you won't have to service the one in the water heater very often, because this is where most of the dust bunnies will get collected. One of my friends is trying to figure out what's the surface area of the filter do I need in order to have a 10-year filter, because apparently nobody likes to replace filters for HVAC equipment, and they expect them to be there. They don't expect a filter for water heaters. We should figure out how to solve that problem. I think, by the way, it's roughly 4 times the opening of this system, so it's not too bad. This is showing a side exhaust, top entry side exhaust, and we basically still have to provide room to make the turn to get up. Why? I want to do the same things. Managing the cold air blowing up along the ceiling allows us to do exactly what we'd recommend doing for HVAC systems. High sidewall ducting works well to distribute air around a building so that people mostly don't notice where it's coming from. And this is the best case we found so far. If you've got a water heater, heat pump water heater with top intake and at least the top exhaust. I don't care so much about the intake side, but if I have a top exhaust, I can get much closer to the back wall. I only have to be able to take out the screw that's there from the cover so that if I want to remove it to work on it, I can. If they put most of the equipment at the front for service access, then I don't need as much on the sides either. That allows me to have a relatively small closet. We have to solve this problem. Why? Starting in 2029, all water heaters above 30 gallons are going to be heat pump water heaters if they're electric, and they fit in really small spaces. We have to start to figure this out. In summary, we want to reduce the distance from the source to the use. I want to improve estimates of peak flow to right size the piping. I want to select pipe sizes that optimize velocity and residual pressure. I want to optimize the volume in the hot water distribution system, or all of it. I want to improve the performance of faucets and shower heads. And for integrated air source heat pump water heaters, I need to manage the cold exhaust air. Here's some useful links. All of them are for NeoPerl because I want you to go find the stuff that makes your buildings work well. By the way, if you use the pressure compensating technology, it helps overcome all the things that you didn't catch in the plumbing, all those extra elbows that you didn't plan on, all the extra bends, the longer lengths, all of that stuff, it helps accommodate by adjusting the size of the orifice at the end at the shower or the faucet. So I want to talk about optimizing the volume for a minute. It's one of my key things this past year, and we'll continue this year. We're on the path to reduce the volume in a building's plumbing water distribution system by 90%. That's a huge reduction. Think about what we did with LED lamps, right? It's a 90% reduction in energy use. And we found it by virtue of changing a technology, okay? So we're able to do the same thing with plumbing. Why is that important? There's an awful lot of work in the United States going on and around the world to help manage Legionella. One of the recommendations is if you're trying to clear out your building, you need to flush it. Well, if you have 10% of the volume, you don't need to flush as much water to clear out the problem, do you? We keep building buildings the same way we built them for the last 60 years and wonder why we still have a problem in the new ones, because we're not focused on the plumbing. So, first part, we have to do architectural compactness. I need your help as architects, designers to get the wet rooms back to back and stacked. I'll happily work with you on that to show how we might make it work, and you'll explain to me why it's so hard, okay? And we'll figure out a way to do it. We need to right-size the trunks and branches using information about modern flow rates and modern probabilities of simultaneity. We need to make them smaller. We can. It's straightforward. We need to reduce the stored volume in the equipment like water softeners. When you have big buildings, you tend to have big water softeners. Why? Estimated based on the peak flow. From where? From the code. The code is off by a factor of 10. We need to right-size things like that. Okay? And then we need to match the diameter of the twigs to the fixture and appliances they're attached to or they serve. If you only have a flow rate of 1 gallon a minute, you do not need a 1/2-inch pipe to serve it. You can use a 1/4-inch tube. That's what the physics says. As long as you have enough residual pressure, the code should allow its use. And by the way, all of these things happen at a lower first cost. So we can save money and build a better building. Given human nature, I think it's our job to provide the infrastructure that supports efficient behaviors. Questions?
There are a lot of questions, and I just want to let everyone know that we're all able to stick around for about 10 minutes after the presentation. So if we don't get to your questions in the next 12 minutes, there's still time if you still have it. I'm going to go through the list that Kim went through. So first up, we have S. Borman. I see you have 2 questions, so if you want to just ask both of them, if you can unmute. Are you still on? Sorry.
Yes, I am.
Okay.
Gary, thank you very much for the talk. It's extremely informative and information dense. It's awesome. 2 questions. The first one was sort of a passing comment that you made about laying the piping inside of a slab. What was the rationale for that? Or not doing it, rather? What was the rationale?
We have a lot of slab-on-grade construction in California, and after a certain number of years, the pipe under the slab breaks, and then you have to replace it. And so either you have to, beat up your slab and cut a big hole in it in order to pull the pipe out, or you reroute the pipe above. So I try to keep supply piping out of slabs or under the slabs because of future maintenance issues. If you really need to put it under the slab, then I want you to put it in a sleeve so that the pipe itself could leak, and then you could pull the pipe back out of the sleeve and fix it again. But I don't generally like it. Okay?
Okay, and fantastic. Thank you. So that was not related to thermal loss, right?
Oh, that too,
It's more...
but it's irrelevant. Thermal loss is 5 times. Get over it. Don't do it.
Okay.
Okay.
And then does that apply for drains as well? I mean, that's a much harder problem that you just don't care about because you can't do anything really.
I do care, but I haven't figured out exactly what to do with it, except to recommend that you figure out how to bring your drain piping from up down outside walls so that you don't have it in the center of your building. So when you do have a problem, you can more easily access it. I don't have great answers for drains. I personally don't like slab on grade construction. I understand why we do it. I just think that there's better things to do. I would like to see raised floors everywhere because then I could access all my underlying infrastructure without a problem.
Thanks. The second one related to heat pump water heaters and the closet that you were talking about. So most of those heat pump water heaters require a volume of around 400 to 700 cubic feet of air to draw from. In that design, obviously that closet's nowhere near that size. Were you pulling that from ducting from outside or inside of the enclosure?
So I think we should be ducting heat pump water heaters to and from the inside. Even my friends in Virginia with very humid air think that the benefits outweigh the problems as long as you manage the potential for condensation risk. The air is generally more useful to you inside, okay, for more of the year. A little cooler in the summer and a little warmer in the winter, but on average, it's pretty good and you're not breaking through the envelope. So I like to see it to and from conditioned space, but if you insist on using outdoor air, you need to go from indoors. You need to suck from outdoors and blow back to outdoors. You don't want to unbalance your envelope. How many years have you spent trying to figure out how to make sure you don't unbalance the envelope by things that suck and blow air? This is just another one of them, and it's around 150 CFM, current product. So it's a pretty big number. So I don't want to imbalance the envelope. So if you insist on using outdoor air, bring it from outdoors and return it to outdoors. If you want to use indoor air, it's from indoor and out. It's indoor to indoor. The 400 to 700 cubic feet is a red herring. It has nothing to do with the volume of the room. It has to do with the energy in the air. I could have a very small volume like that closet and I could have it unconnected as long as I put some form of heat into the space. And the heat into the space has to be equal to the heat rate of the heat pump. Otherwise, it's going to bring the room temperature down. When I design for hot water use, I don't presume that I know how much hot water they're going to use. That's what 700 or 400 cubic feet are telling us. Someone's said it's acceptable for a certain amount of daily hot water use. I have no idea how much hot water people are going to use. And of all the people on this call, you'd ask me, how much are they going to use? I don't know. It varies every single day. And in some occupancies, we put residential scale water heaters where they use a lot of hot water. Water heater doesn't know where it's going. We want the energy in the air. Volume is not relevant. Airflow, energy in the air is. Okay. I hope that helps.
Fantastic. No, that's fantastic. And in your research, have you any sort of updated guidance with respect to that sort of sizing? Or is there anything out there better than manufacturer specifications, which are clearly wrong?
We're working on it. So I expect we'll have better guidance in 6 months. But I do know this: if your fan is if fans are about 150 CFM, as long as you make sure you direct the airflow with very little pressure loss using, nice round smooth duct, not too many elbows. You've made sure you've done it. Figure you've got a 10-inch hole or 8-inch hole. You need an 8-inch duct. You want to make it neat, clean, short, and smooth, right? All that stuff. You'll get 140 instead of 150 CFM. You've not restricted the airflow through the heat pump. You've done good. You just have to connect it to a space that has enough energy in it, because you're not trying to heat the space in the room directly. You're trying to heat the air going to the heat pump. Okay.
Thank you very much.
It's a CFM problem to an energy source. All right. Go ahead. Next question.
Rishi Raj, I think you have a few questions. Do you want to go through them? You want to ask them all and then let Gary answer them? I think you're still here.
Yes, I am. Yeah, thanks a lot. Thanks a lot, Gary, for the presentation. I apologize. I'm fighting a flu these days, but I had three questions. I think one of them you answered during the presentation, so I just have two in the end. The first one is, what happens when you exceed the demand calculated or sized by the calculator you presented? Is it actual pipe failure that we're talking about or something else? And the second one was best locations for heat pump water heaters. So I know that they thrive in warmer locations. So for larger commercial or residential buildings, would a telecom closet or like pump rooms or other warmer locations be a good spot for heat pump water heaters? And how can we best centralize them to make sure that we follow the rules that you're trying to present?
Okay. So, and I think I saw another question about, okay. So working backwards, if I miss something, you'll just correct me and I'll come back to it. The closet, your idea is exactly right. You want warm air. They're rated for efficiency at 67.5 degrees and 50% relative humidity. If you've got a closet with 100-degree temperatures in it because you've got all these servers running, use that energy source. You may not want to locate the water heater there, but you certainly want to bring the warm air from there. And you may as well send back the cold air so that you can cool the room. So you may or may not want to put the water heater near the electrical stuff, but you certainly want to use the energy in that air. So that's absolutely a great idea. If you've got commercial refrigeration, suck behind the refrigerators, blow back to the refrigerators. You're using extra energy. You're going to dump the heat anyway. Use it for something else. That's the right strategy. The centralization question has to do with where did you put that room in the first place, and that's set up long in advance of designing the plumbing. So we have to go back to the beginning and have this heat pump discussion and the pipe discussion very early on in the design. What were your other ones? Water heaters in the telecom rooms. I like that question. It was a good question for that.
So
What
I
was the
just
other
had
one?
just one more, which was related to what happens when you exceed
Ah,
the design calculation for the pipes.
right. So what happens when you exceed the design calculation today in modern plumbing? By the way, these are all 99th percentile. So some 1% of the time we're expecting it might be higher. What happens is the events are short in all evidence that we have. The exceedances are very short in duration, and their effect isn't to make the pipe fail, it's to lower the pressure in the building. And so one of the reasons that I like to put pressure compensating flow regulators for faucets and showers is that means people using the water get first dibs on available pressure. So if you have an exceedance or a high flow rate in a portion of the building that reduces the residual pressure at your fixture, you won't notice. And if you do have a lower pressure for a minute, so what? It'll take a little longer for the toilets to fill. Generally not a problem. And currently the water demand calculator is providing a factor of 2 margin of safety. We don't want to get too much closer to the bone at the moment because there's a bunch of stuff we don't understand about what's really happening in our plumbing systems. Next question.
Thank you.
You're
Great.
welcome.
Thanks. Mark Houston? Trying to get through this list. Is this person here? Sorry. If we, I just want to acknowledge also that it's almost 1 o'clock. So if you need to hop off, feel free. The recording, I think, will continue till we end of Q&A. So as Kim mentioned, the recording will be up tomorrow. So you can catch the last bit. Mark, are you here still? If not, Mark's question was if you could share the flow calculator website.
Sure. I will get to that right now.
And then
You should be able to capture it here on the screen. IAPMO Water Demand Calculator. I always Google it. I just
yeah,
find it
I'll
every
Google
time I
it
need.
and I'll drop the link in there.
All right.
Silas, are you here?
And there was one more question about the 6 things I wanted to be sure that you do, and I'm putting the summary slide back up so you can see it.
Yeah, I'm here. Hi, Gary. Thanks so much. I always enjoy hearing your talk. I've never heard you, I don't think, mention drain heat recovery devices, so I assume you don't have much of an opinion of them, but I'm just curious. Thanks.
Thank you for the question. I do talk about drain heat recovery. hard to figure out how we're going to integrate it in many buildings. The reason it's hard is because we don't have central core plumbing very often. And so drain water heat recovery is in residential applications most effective when you're taking a shower, a simultaneous need for hot and cold water. Okay. Or hot water while you're running water down the drain, which is what you need. And so if the best case is that you can have is to have central core plumbing, which is what I'd like to see, and then the drain water heat recovery can both send water to the showers that are being used and to the water heater that's heating them. It's the way to optimize the total amount of energy you capture from the system. I'll have to add that in when we start getting centralized plumbing. I'll put that back into the mix. Right now, with decentralized wet rooms, it just doesn't help very much.
Great, thank you.
Thank you.
Great, thanks. EG, you're up.
Hi, yeah. I think there was, can you hear me?
Yeah, we can hear you.
Yeah. Thanks. Yeah, so you were talking about ducting the discharge air from the heat pump. I mean, I think it's come up a bit, but I'm assuming there's some consideration to where that is delivered, or is it not necessarily a comfort issue for?
It is a comfort issue, and it's going to an adjacent space. I've shown it in the simplest case where it's coming out of the closet right above the door. And that closet is most often in a hall if it's a closet situation with water heaters. At least that's been my experience. Okay. And so it can be a closet to any space, but it's often into a hallway. So if it's in a hallway, you don't want to blow the air straight out at the opposite wall. It's just going to bounce off and not do much good. You want to blow it down the hall, and you want to blow it up near the ceiling so it doesn't hit people directly. It wants to mix before it hits people. If it's going into your living room, you do the same thing. You want high ductwork anyway. By the way, if you've got a mechanical room in your basement, if you have a mechanical room in your house or your basement, and you've got your heating and air system in there, the air handler for it, you could connect the exhaust of the heat pump into the return of the HVAC system and let it move air around the whole building. Okay. You want to close couple it because you've got a perfectly good distribution mechanism called your air handler and your duct system. Best case I've seen is out of a friend of mine, Gary Nelson in Minneapolis. His basement has a mechanical room. The mechanical room has a doorway, but no door. Air comes down the stairs from the main house into the basement. It gets pulled into the mechanical room by the air handler, and it gets reheated if needed or cooled if needed and shipped around the house. Okay. He has an air-to-air heat exchanger that brings in fresh air from outside and exhausts the bad air from the bathrooms. Okay. That's what he's done. Sounds pretty normal. He does not have separate ductwork for this. I know that's going to bother some of you, but this is Gary. He knows airflow. Okay. And so he spent good money on making sure his HVAC ductwork was tight and insulated and proper with high sidewall vents into each of the rooms or ceiling vents into each of the rooms so that he could properly pull air and distribute it properly in the buildings. All good so far, right? His air source heat pump water heater sits right next to the mechanical room. It uses return air from the house to heat the water and dumps the cold air on the floor of the mech room, which gets sucked up into the air handler. By the way, that air handler fan runs 24/7 at about 20 watts, 25 watts. He was going to pay for the air distribution anyway. So now he's close coupled them. The idea is to close couple the cold air so it doesn't inadvertently settle on things or blow on things and lower the temperature before it becomes well mixed. I hope that answers the question.
That's a great strategy. Yeah, thank you.
All right. You're welcome.
Thanks.
What else do we got?
I think Bart's question was about the slide with the 6 things which you shared. So thanks. I'm gonna skip over that one. The next question is from Paul, who had to leave the call. So I'll just read his question. He said, I saw the slide showing the difference in diameters between the different types of PECs. Other than those diameters, do you have any other recommendations between different types?
No, the real recommendation, those are the most commonly used for plumbing in the US at the moment. Some people are starting to use stainless steel and some are using other forms of plastic, but those three are the most common today. And we can debate whether we like plastics or not. That's a whole different conversation. What I want to say is that what matters is to ensure you have enough residual pressure at the end of the pipe. That's what matters from a flow point of view, performance point of view. And the way you do that is by minimizing length and resistance, right? You want to minimize the resistance along the path. That's dependent upon the flow rate along the path. So we can make any pipe material work within reason. You're going to have an awful lot of consternation if you try to use pipes smaller than 3/8. And in some jurisdictions, you have trouble with 3/8 just because the jurisdiction doesn't think it works. We need to have conversations about that. I'm happy to help you figure out how to sell the idea. Okay. It's, by the way, the codes allow it. You're allowed to ask for alternate methods and means. You just have to ensure you're going to have enough residual pressure. That's generally the bottom line.
Great. Trevor, I saw you turn on your camera. Do you want to ask your question? Trevor looks like he's waiting for this answer so he can go apply it in wherever job site he's at right now.
Yes, I saw Allison Bailey's write-up about the manifold system he did in his home. I found that very interesting. I was curious if you have a recommendation on when to implement that versus like a source demand, like a recirc loop.
Yes, I do. Only in very tight configurations of the wet rooms. So, Trevor, you're in a room right now, right? Many people are in an office that's around 10 by 12. They're sitting in their office at their home or wherever they work. That's a typical size, right? To get from a water heater in one corner to the other corner of that room, you have to go up, across, and down the other side. Mostly we don't run plumbing diagonally because somebody put a light in our way, or a duct in our way, or a drain in our way. Do you follow me? Plumbing tends to run rectilinear with the building, and I prefer that. Okay. Why? When it breaks, I know where to find it. Okay. And so it's just easier to figure out. So it turns out to get from one corner of a 10 by 10 room to the other corner with a fixture, you need 5 feet up, 10 feet plus 10 feet. That's 25 feet. And I have to come down another 5 to 10 feet. I've got 30 feet of pipe to get to the other fixture. If my manifold is on one side and my twig is 30 feet long, I don't have a prayer of getting hot water efficiently, do I? So you want to have, you can use home run manifolds in cases where you've got very short runs of plumbing, either vertically or sideways, less than one room. You want to only use one wall. Otherwise, they will not be effective. The other thing on manifolds is you have a trunk from the water heater to the manifold. How close is the manifold to the water heater? Is it 3 feet away, 10 feet away, 5 feet away? Follow the pipe, right? That becomes a lever, right? Because it's 3/4 or 1 inch pipe, and it's got three times the water as the 3/8 pipe does per foot. It's a kicker. If you want to do a home run manifold, the best case I've ever seen is to make a copper manifold on the top of the water heater and let the manifold remain hot, insulate it really well. You're leaking heat out of the water heater, but you insulate it really well. That way, everybody is only getting energy from the twigs. And then you have close coupled plumbing, so you're within 20 feet in 3/8 tubing. You can do pretty well. Short lengths. Okay.
Thank you.
And
Gary,
That helps.
on insulating hot water heating pipes, do you have any preferred brands or systems? Do you like old school fiberglass with paper on it, or are you more of the more advanced elastomerics?
I'm going to remain agnostic on this. I want it continuous. Okay.
Over fittings and everything, and
over fittings and everything. So it turns out if you follow the physics, you don't want screen doors in the submarine. So every time you have an uninsulated piece, all the heat, 90% of the heat leaks out of the places that are under insulated. Well, it's not true exactly. You get the point, though. You have an overwhelming amount out of the parts that aren't insulated. So having 1/4 inch or 1/2 inch insulation everywhere is better than having 1 inch somewhere and none other places. You're better off with continuous at some amount. If you're using flexible pipe and you're not putting in hard 90 elbows, You can sort of, it's hard to bend fiberglass. It's easier to bend the foams. The closed cell foams don't shrink in length as much as the open cell foams do. We've seen pipe insulation installed where there's 6 inches missing every 6 feet. Like perfect. Someone like did it intentionally. It just shrunk. If you're worried about shrinkage, do 2 layers or pick a different material.
My last selfish question is, has any manufacturer stepped into the solar domestic hot water game in the US that you know of?
No, I don't know of anyone. The industry is enamored of solar electric. One of the reasons is that water on your roof tends to break and leak, and it's a real pain in the you-know-what. And so it's a harder sell because we still haven't figured out how to close couple stuff and how to prevent the freezing problem or the overheating problem. There's a couple that have, but that's for another day. We can have a longer conversation. We can bring other people in for that one.
Awesome.
What else do we have? I saw a question from Chris Laumer. Are there any others?
There's Michael Dudek has a question, Chris has a question, but I just want to kind of like remind everyone that it is 1:11. We as this is an exciting conversation. I recommend that folks reach out to Gary directly. And then this Friday, the AMA is also on domestic hot water. Unfortunately, not with Gary, but I think, there's more opportunities to talk about it. So Michael and Chris, if you guys can quickly go through your questions, and then Kevin and Gary can share some final words, and Kim can share our last little reminder of events coming up. And if you have to hop off, we understand.
This is Mike. 2 real quick questions. PEX, isn't it true that you have 30% less heat loss through PEX than you do copper?
No. It's not true. At least not entirely. Here's the problem. No, it's not true. It's just not true. So the reason people say that is that PEX is as a material is better insulating than copper, for sure, right? It's plastic versus a metal, all good. When you build a building, however, all that means is that the heat gets out of the pipe quicker in copper, but it gets from the inside of the wall of the pipe to the outside of the wall of the pipe really fast in copper, like that.
Yeah.
In plastic, it takes a second instead of a millisecond. So it's there. Once it's there, you have conduction, convection, and radiation taking over the process. And it turns out that copper is a poorer radiator than plastics are. So in fact, plastic pipe loses heat more quickly in a building's plumbing system than copper does. Very confusing, very annoying,
Good
but
point.
true.
No, very good point.
Okay.
Next question.
Go ahead.
Electric water heaters, tankless. Have you ever seen any work?
That's not quite the right question. The question is, for how long do they work? So you can make them work, and I've seen many that do, but I have a favorite story about my dentist's office. I went to the same dentist for 20-something years. I never got hot water at the sink. I looked underneath, and it had been disconnected 20 years ago. They had an electric water heater for the sink. It turned on and it worked for a while, and then it eventually stopped, and they just figured no one cared, so they didn't fix it. Electric tankless water heaters are generally a very good product for certain applications. The dilemma is they're very high intensity of heat rate, and that causes problems with anything wrong with the water. The water quality causes the electric elements to fail. And so you have to think about that carefully if you're going to do it.
Quality water is the answer.
Yeah, and that's a real problem to fix properly because it varies everywhere.
Yep.
I have good friends who make them, and I like them, and I like their product, and it works in certain places really well. They also have really high electric heat rates, so they draw a lot of watts. Mm-hmm. And if you're worried about that, you want to do something other than high heat rate. Okay, one more question, then I'm going to finish for the day. Somebody else?
Shefali, I think you're on mute, but we had a quick question from Chris.
Yes, thanks.
Hey, Gary.
Go ahead, Chris. Hi, Chris.
Hey, it's more of an update for you, but also to comment to those watching about what to do, because I know what I did, but we had this passive house we're doing in Atlanta, the shower heads in all of the bathrooms. The owner was concerned that when he moves into the house, he's not going to like the pressure of a low flow fixture. I said there are fixtures out there that make it sort of give you the sensation of higher pressure without the higher pressure, but he still wanted to have it plumbed for a higher flow rate fixture. So we said, sure, we went from 3/8. By the way, everybody, we did 1/4 inch 3/8 on this system. We insulated everything to the inch. And we also, our plumber, Gary, thanks for your encouragement, got our plumber to put radius in all the turns so we have no elbows in our hot water lines. They're all large sweeping turns. Amazing. Plumber did an outstanding job. But I just wanted you to comment on this, when you go from, because this happens, people move in, they say, I don't like it, I'm going to go to a higher one. Just let you comment on that, because again, I know what we did, and what you would tell me to do, but let people hear about it.
Okay, so this graph should tell you what we need to know. This table. These are flow rates and velocities. And so if you have a 2.5 gallon per minute shower head, it means you have 2.5 gallons per minute coming out of the pipe where the shower head's attached. You're not going to have 2.5 on either side because they have to mix. But we'll assume you have like 2.4 because it's easy to see the numbers here. That's 8 feet per second in 3/8 PEX. In 3/8 copper, 8 feet per second is 3.6 gallons per minute. If I only have to have two something, I'm going to have 5 or 6 feet per second. I won't have a problem with 3/8 tubing. Okay? It won't create too much residual pressure is the point. Other things might. So if you are worried about it, technically you could use 3/8 tubing for that purpose, because the flow rate on any given side is not going to be the total flow. If you want to stay at 1/2 inch, velocities are going to be low, and that has other issues, but at least they'll be 3 or 4 feet per second. Okay, 3 to 5. So I think you did the right thing by allowing it to go for the shower heads to be 1/2 inch and just not fight that battle. We need more evidence. If people want to help me set up demonstrations, I'll help you set up demonstrations so we can do videos and we can explain it to the industry. People just don't follow the physics well.
No.
And so we have to share it.
They need to take the shower to know for sure. They need to feel it. They need to say, okay, but by then it's too late. So
yeah, it's way too late. Yeah. So that's why I like pressure compensating flow regulators so much. It overcomes all the dumb stuff we didn't plan on.
Yeah.
Thank you, Chris.
Good call. Yep. Thanks, Gary.
All right.
Awesome.
Back to the hosts.
I think we are at the end of questions. Kevin, do you have any final words?
Just another wonderful presentation by Gary. I can't wait till number 5 where you're presenting on the accelerator. So let's talk domestic hot water solar applications. It would be awesome.
Okay. Thank you all very much. Have a great day. Bye now.
Bye, everybody. Take care. Thank you.